Hello, and welcome to my Project 2.1 R2R DAC. Today, I will be explaining how my 16-bit DAC works using two concepts. The first is Thevenin equivalent circuits, and the next will be superposition theorem. I hope you enjoy listening to today's video. So first, understand the DAC. We're going to look at the total resistance of the circuit. This can be done with Thevenin's equivalent circuits. To make it easier to understand, I'm going to be explaining this on a scaled-down version of the DAC. I have a 16-bit DAC, but to explain the concepts, I will be using a diagram of a 4-bit DAC. So Thevenin basically says that in a circuit containing linear elements, you could essentially break the circuit at any point and replace the break with the open source voltage that would be there and one resistor. So here we have 10.2K and 10.2K. So this in parallel, so this will be replaced with one 5.1K resistor in series here. And we need to short out the voltage sources, so ground them. So then when we replace these, we get one 5.1K ohm resistor in series with another 5.1K ohm resistor. And since they're in series and they're the same value, this can be simplified to one 10.2K ohm resistor. And if you may notice, now that that's been replaced, these two are in parallel, just like the first time. So we know this can be simplified again to one 5.1K ohm resistor. So if we look at that, that would be this. So then again, it's like it keeps repeating itself. So here we have a 5.1K ohm in series with another 5.1K ohm. We know this is 10.2K, which will be in parallel with this 10.2K. which can be replaced again here with another 5.1K. So here it simplifies again to this. So it's two 5.1Ks in series with each other, and those two are in parallel with another 10.2. And we know that can essentially be replaced by this. So it's again 10.2K, 10.2K, which is this. So using Thevenin's circuits equivalence, we can simplify the whole resistance of the circuits or impedance to one 5.1K ohm resistor. In the Thevenin equivalent circuits, we can find the voltage contributions for any given binary code here. So superposition basically states that we short out all the voltage sources except for the one being calculated for. So in this example, we'll do bit 0. And then you do this for each of the sources that are on, and then you add them up. So for bit 0, we have a voltage here, 9 volts in this circuit, across two equal resistors going to ground. So we know here will be half of bit 0. So this can be replaced with one resistor, and this is from Thevenin. We know that, and B0 divided by 2. So now we have a similar looking circuit with one 10.2K, because these add, and then in parallel with another 10.2. So we know here the voltage contribution will be half that again. So we have that replaced with this, and now it's bit 0, a quarter of bit 0. So now again we have the same thing, 10.2 and 10.2. So here we would see an eighth of bit 0's contributions. So then this can be simplified again to, we get the total contribution of bit 0 would be 1/16 of the input voltage going through a series resistor to the out. So, and then we do this for each of the bits and then add it up to find the total voltage for a given input. Now, understanding these two concepts, we can turn back to the 16-bit DAC and look at the breadboard prototype to understand how turning each of these switches increases the voltage incrementally like this. Observe how from the least significant bit to most significant bit, the voltage increments by increasing values. As you may notice, for the first 8 bits, nothing really goes up in the voltmeter. And this is due to the fact that their contributions are so low, 2 to the negative 16th, that the 3-digit voltmeter cannot display this. Thank you for listening, and I hope you learned something about the DAC.